Hello everyone, my name is Daqian, a PhD student from the University of Toronto. Today, I'm going to introduce our paper, Property-Based Entity Type Graph Matching. Generally, we model the schema of a knowledge base as a set of entity types. For example, person, where each entity type is associated with a set of properties, for example, age or height. We call it entity type graph or Etab graph for short. In this paper, we aim to match correlated etypes between etype graphs since it is a crucial step for knowledge reuse. Most etype graph matching approaches exploits label-based methods such as character similarity matrix and synonym analysis, and also we have structure-based methods, which is efficient in some cases. However, focusing too much on the label of etypes may be counterproductive. For example, an eagle can be labeled as bird in a general purpose ontology and also can be an eagle in a domain-specific ontology. We find that structure-based matching may also lead to wrong conclusions. For example, the superclass of entity etype eagle can be animal in etype graph 1 and it can be bird in another etype graph 2, which will not help to match the target etype. However, the properties used to describe the target etype will be similar even it has been labeled differently or assigned in different structures. With this inspiration, we consider if properties can help to match etypes. It is a fact that as one of the features used to describe an etype, the properties are used to intentionally define an etype, which is independent of the specific label and also the structure. This gives us opportunity to improve etype graph matching based on a new feature, that is property. At the same time, it is pointed that more specific property will contribute more to identifying the target etype. This means we could cognitively measure the similarity between etypes by distinguishing properties with different specificity. With these two intuitions, we propose a set of property-based similarity measurements, which aims to measure the correlation between two etypes based on their corresponding properties. In the initial phase of our method, we formalize an etype graph as a formal concept analysis lattice, which provides a formal way to present the etypes and their corresponding properties. Compared to general FCAs, our formalization uses a set of etypes but not a set of entities. An etype is considered to be described by a set of properties in an etype graph. We formalize an etype graph as etype property correlation map. Here, the example presents a hierarchy of an etype graph. In each box, etypes are presented in yellow and their properties green. We can see all these etypes in hierarchy are encoded in the FCA context. As we have the FCA context, we consider not only the associated properties, but also the non-associated properties contribute to describe etypes. And thus, we introduce the non-associated properties into our FCA context and distinguishing two more different cases for better presenting the FCA context. In this example, we can see that the value box with circles represents the properties is associated with the etype. The value box with crosses means the property is not associated with etype. UN represents a special case that the property is not associated, but associated with at least one of the subclasses of the etype, of that etype. Thus, UN means the property is undefined for the target etype. For example, academic award is associated with the etype artist, but undefined for the etype person. For benefiting the follow-up calculation, we encode these three correlations as property WP, here as shows. We need to notice when we have two candidates etype graphs waiting for matching, we need to generate an FCA for each of them. Our property-based etype similarity measurements is inspired by the fact that properties with different specificity will contribute differently to identifying etypes. When measuring the specificity of a property, an idea is to horizontally compare the number of etypes that are described by a specific property, namely the shareability of the property. If a property is used for describing diverse etypes, it means that the property is not highly characterizing. For instance, we can find in FCA, the property name is used to describe person, place, athlete. Duly, if a property is used for describing a few etypes or even only one etype, this means the property can be regarded as highly characterizing. For example, property settlement is specific for etype place. Based on this observation, we consider the specificity of a property is related to its shareability. Therefore, we propose as P as the matrix for measuring that shareability. In the function, we take P as the input property that's waiting for measuring. NP is the number of etypes that are described by the input property in the knowledge graph. Thus, NP is greater or equal to 0. Lambda presents a constraint factor for the function. The parameter WP is what is about how we encode the FCA values. Then we can calculate the horizontal similarity for two etypes based on the function SP. EA and EB are two candidate etypes from the entity graph A and B respectively. SP function means the property specificity of PI in etype graph A and B. Proper E refers to the number of properties associated with the specific etype, which is used for a normalization purpose. Okay, as we know, etype graphs are organized as a classification hierarchy, such that upper layer etypes represent more general concepts. Lower layer etypes represents more concrete concepts. Correspondingly, properties of upper layer etypes are more general, and properties of lower layer etypes are more specific. We assume that these specific properties will contribute more to the etype identification. For instance, in the figure, as a lower layer etype, artist can be identified by the property academic award, but not by the property name. Therefore, we propose LP as the metric for vertically measuring the property specificity. We take P as the input property. WP is the FC encoding value. Theta is the constraint factor for normalizing the range of the function. The layer E refers to the layer of an etype. Thus, as soon as we have LP here, we obtain the vertical specificity for a property. And then we compare to ESH, the vertical similarity ESV has a very similar expression. The difference is we use function L instead of the function SP. After we sum up all the property specificity, we obtain the etype similarity ESH and ESV between two etypes. This table provides some representative examples to show the etype similarity ESV and ESH in OAI conference track. We can find that etype matching pairs like paper, to contribution has higher ESV and ESH score, and non-matching pairs like person to conference documents has a lower score, which means the similarity between etypes is positively related to our metrics. Okay. This processing chart refers to our Etab matching framework, which mainly consists of two measures, the property measure and the Etab measure. After parsing the input Etab graphs, properties are first sent into the LP-based property matcher, which matches correlated properties by their labels. Then we generate the FCA contest according to the etypes and correlated property pairs. In this phase, we will also generate our property-based etype similarity metrics and then send them to the etype matcher. We develop a machine learning-based matcher which consider etype matching as a binary classification task. For better matching results, label-based similarity metrics and our property-based similarity metrics are all exploited by the etype matcher. Finally, the etype matcher outputs the correlated etype pairs as a result. Our evaluation focuses on ontologies that contain etypes associated with a fair number of properties. As a result, we select two cases. The bibliographic ontology dataset for training and the conference track for testing. We select the training and testing set from different cases since we aim to prove the adaptation of our approach, also to prevent our approach from overfitting. For better evaluating the validity of our approach, we apply 4 different machine learning models, which are random forest, HGD classifier, decision tree, and logistic regression. We have compared our work with state-of-art matching methods. They are FCA map, AML, logmap, and logmaplet. We calculate precision, recall, F1, F0.5, and F2 measure. We can find here our methods show competitive results in most of the cases and overpass the state-of-art methods on a part of the metrics. We also set ablation tests to show the validity of our designed metrics, ESH and ESV. We test on the backbone model B, which was trained only by lexical-based similarity metrics. We also test on the model with ESH, ESV, and both ESH and ESV, respectively. Note that the backbone B refers to ours SGD classifier in table 2. We can see here with the using of our metrics, especially with the using of both metrics, the performance improves a lot compared to the backbone version. Okay, that's all for my presentation. Thank you very much for listening.